Hello everyone, my name is abucnasty, and in today's video we're going to be going through optimizing my Logistic Science Pack blades. These are, frankly, as I've been thinking about it, I've been not looking forward to getting back to this, or I guess I have been looking forward to it, but this is the worst build that I've made in this series, and I'm quite frankly a little bit embarrassed by it. I went a little bit overboard and decided to use rocket silos for more things than really needed. This worked out pretty good in the military science build like we talked about previously, but this doesn't work so well here, and I'll kind of explain why. So if you think about what am I transporting through these rocket silos? Well, I'm transporting in here effectively just the items to process everything inside here, so transport belts and inserters. This is fine in theory, especially if they're stacked on belts, but the rocket capacity of inserters is limited to 50. Transport belts are a little bit bigger at 100, but now they're sharing their space with inserters. So technically inside any one of these silo chests, and that's what we're using these for, I can only fit 50 of each at a time. So it's already really small. So it's just 2-3 swings of a stack inserter and you'll be close to the number. You'll be at 48 with 3 swings. So, and at the rate that this is consuming it, that means that you're constantly having to cycle and to set the filters, and it's just a very tight control to just make this work. So I already know that that's just a bad design. Plus the first silo, I'm also using as a intermediary to pass copper cables and electronic circuits around. So it's great because I can save on just having one building of each type, but it's a lot of extra complexity and a lot of circuit control decisions that need to be made just to make this possible. And so as I've been thinking about it, I'm going to try to get away from rocket siloing for things that have really small rocket capacity or that aren't just immediately getting destroyed like on Fulgora. So that also being said, this build is also terrible because it's decent in the sense that we need less furnaces here because the ratios worked out in such a way, at least because of this terrible build that I made here, that I could do a 3 builds to make 4 lanes. But that's because these transport belts, where I'd want this to be, like, in essence, fully stacked, this doesn't make quite 2, but combined all 3 of these here, if I grab these and go 0.25, these make just over 4. So this is just bad. These have only effectively 4 beacons surrounding them, where we can fit easily up to 12 beacons around them, so we can drastically reduce these. Anyway, I'm going to stop ranting about my prior self, and we're going to try to optimize this. So the point of today's video is we want to build, just like the other videos in this series, redesign the science, start from scratch. Let's take some existing concepts that we've talked about in previous videos, apply them here, and then create a few different designs. My plan is I'd like to have 3 different designs for us to test in the end and then benchmark, and then ultimately the one that wins is the one that I'm going to put in the video at the end and show it running in my base. So without further ado, let's just get into the video. So as always, we're going to start with the bill of materials. These are all the buildings that we're going to use today. These are the best buildings for their respective type that also still allow for higher quality crafting. We're not using foundries for the iron plates because there is no recipe for it, unfortunately, for selecting a different quality. So we're going to have to use furnaces to go and create uncraft the uncommon, and that also means that we're going to be needing to use uncommon ore to smelt. So how do we create that? I previously went through and posted a deep dive video on this contraption that I've created. I've made it slightly more complicated than the last time that I've talked about it, but I've made one slight optimization to it. I added an RS latch so that if the downstream material is slower than 240, that this miner can start turning on and off and cycling. So in practice, across all the different sciences that are in the base, in theory, this should help by cycling on and cycling off the different materials that are being crafted. And the way that I can demonstrate that, I can just put a yellow belt down here just so we can show this. When this slows down, this doesn't need to be running at 240 per second. Now it's, a quarter of that speed. So you should see this cycle on and off now based on the load that's down there. And the way it just does that is it just monitors the contents of these to chests that are being inserted into. And whenever that value happens to go, basically being less than 200, it will then say and send a signal that will say, hey, I'm not sleeping anymore. And the moment that it gets to being greater than or equal to 400, which is the maximum size in these chests, then it will go ahead and trigger the sleep condition, and that's just looped in and on itself. And then so whenever it's sleeping, it waits until it's less than 200, and then it will kick off. And then when it's not sleeping, it just runs until it gets to 400. So next, the one thing that we need to do now is we got to design what is the final output. So I always like working backwards. So how do we make the logistics science pack and start from there and then work all the way backwards until we get to the raw materials. For the interest of time, I've already designed what the final output's going to be using the lead follower concept here. However, one thing that I wanted to note was this is effectively the same, so you really haven't missed out much. If you want to see me design this from scratch, I did this already for Red Science. The only difference here is that it's one more assembler, so instead of it being 5, it is now 6, and that's just because of the crafting time. So an interesting that I noticed was there was an instability here with this particular input. So I started to notice that there's gaps occasionally. Even though we have enough back pressure down here, we're monitoring this output. This is constantly being fed. And you could basically go and say, hey, I'm going to go ahead and delete this here. Let's let it all stack up. And that was my initial assumption was, okay, I got to wait until all the lines are fully saturated here. And then let's go ahead and kick this off and run this for a while. But I still, even though I did that, I started to have these tiny little gaps that are forming in here, even though this is fully back pressured and it doesn't have an issue. So I started to wonder, why is that happening? And it took me a little bit of trial and error, but eventually I kind of came across what the issue was in the end. So there's this slight deadlock that can happen, and it just happened there for a blip, where it stops for some reason. And so the way that I kind of replicated this was I said, okay, if the inputs here, let's go ahead and completely stop this, and wait until this fully backs up here. So you're seeing here, this stops at 48. Sometimes it stops at 48, sometimes here at 32, sometimes it stops at, 48, and it all just kind of depends. And the reason it's happening is whenever this inserter is considered active, and since we're controlling it, we're turning it on and off exclusively, the assembly machine will not craft an item again until all of its output contents are finished whenever there's an interrupt from the inserter in front of it. So whenever you actually physically disable it, the assembly machine will say, hey, I'm done crafting. I need to fully output all my items before I can continue the craft again. So in here, you're seeing this as 48 items, right? So naturally what I kind of decided on was, okay, so to alleviate some of the problems downstream, an easy option I could do is just say, hey, whenever this is greater than or equal to 24, to give these an extra tick to swing in that case, that should be an easy solve. So I went ahead and said that. And that's totally fine because as we know, the stack size of this can go up to 48. So what I'm going to do here is I'm going to keep this the same because this will otherwise trigger the condition of the deadlock that I was talking about. And this is starting to run. So it immediately emptied. This is fine. So what I wound up doing is I said, here, we're going to set this to 24. And the moment that I did that, I noticed, great, I'm not having any more gaps in this belt. Awesome, I've solved it. And then I went and deleted this. This all of a sudden backed up, and what happens, and this is a wonderful scenario here, I then went and I said, okay, and I'm glad I tested this, let's turn this back on. Oh no, why did everything stop crafting? So that whole problem that I talked about before, which was plaguing all these assembly machines down here, the root cause is this. So right now, this machine is at 16 items. And the logic here is saying I wanted an extra buffer of 24 items, which solved my downstream problem of the little interrupts and the occasional starts and stops. But now, because this assembly machine has 16 items on the output and it can't finish and put one more item in here until this is pulled out, because the game is saying, hey, logically, this should be able to grab all 16 items, but it is disabled because this is not greater than 24. So because this needs to fully empty its contents, it cannot do it, and this logic is preventing it, so it creates this deadlock. So one way that I've said, okay, well, I want to keep this condition. I'd like it so that when it's greater than 24, that's when I'm going to do it, and I don't want to read the contents of this inserter, because that would be an easy option. So I could hook this back in, I could read the hand contents, and I could check that. But that's not going to do me any good here, because I'm still going to get into this situation. So a simple workaround that I did to deal with this problem, and you guys might run into it as well, is I just said, okay, well, I'm already reading the working condition. That's that nice little pink icon that is showing, because whenever it's 0. So what I added was an extra condition here. So I said that, okay, if the working signal here, and I'll just completely pause the time, if working signal is equal to 0, and this has any contents in it, I could set it to 16, but it doesn't really matter. This is the deadlock scenario that I want to prevent from happening. So when this condition happens, I want it to shortcut and say, cool, I'm going to go ahead and emit for one more tick a check mark. However, I don't want to remove this condition here. Otherwise, anytime that there's any item of logistic science packs, this will swing, and that completely short circuits or removes the ability of all the UPS savings that we get from using this lead follower concept. So in order to deal with these starts and stops and have the slightly higher buffer on when it needs to be outputting items that exceeds the stack size, we created this condition. So now if I resume the game, it can easily get itself out of that deadlock scenario, run again. It'll take a little bit to back up again so we get back to the normal state. But once it does and we're running fully again, now we can get out of that scenario and prevent any of the little belt issues that we were happening before. So this is a convenient thing that I wanted to demonstrate, and that's why instead of designing this, I wanted to go into this concept, because I think it's really helpful to understand that there is a potential deadlock scenario that you can get into when you're using a lead follower concept over traditional clocks. So there you go. That is an easy way to deal with that problem. So the next thing that I want to get into is let's go and craft all the materials. What are we going to need for these inputs? And let's get into that next. So let's design the actual final module that we're going to need here. So what I'm going to do is let's make it the exact same width as this, because that'd be kind of a nice thing just to have, is if they were the same width, that would make this easily tileable. Man, why is that such a hard word? So I would like this so that I can just easily take this whole design and just copy and paste it right next to it. That'd be nice from a space efficiency perspective. So let's use that as our constraint. So I'm going to go and say I'm going to make a little bounding box. This is going to be the amount of width that we have. And let's also give ourselves a little bit more room. So let's just go up here. That's fine. Something like that. That's fine. Perfect. So let's move that up here. So first things first, this has a tile width of 5. So let's just put this somewhere down here. So that perfectly aligns to be in the center. Also, this is going to be making an excessive amount. Like we said, we only need per side 60 items. So really we're only going to need to make 120 items. So I really just want one stack inserter pulling or bulk inserter pulling things out. So this is perfectly fine for our needs here. So we don't need more than one of these buildings. One is going to be fine. However, we are going to need more for assemblers and for gears. And the reason is because gears are going to be shared between two things. It's going to be this and this. So we're going to need something that inputs in here. And let's just move this up a little bit. Let's try that. So we can have this. We're going to need an output that is coming from this here, which we could have going up. I don't know. We'll deal with that. We're going to need an output there. And ideally, I'd like this to somehow do this here. Perfect. And then I'm going to need, this is going to be outputting on the outside lane, so there needs to be something that goes on the inside lane. So I guess I could do this and wrap it around here. Well, not necessarily that. We could do this, and that's probably fine for what we're going to need. So we can keep this here. This will output like that, and that'll be fine. Okay, so then that kind of covers the outputs. We're going to need input here. We're going to need both of these are going to need iron plates. So, and this is going to need probably more than this is going to need, because this is only going to need 60 items per second, but this is going to be feeding both of them. So let's go ahead and add a second one, because this is already going to be needing to create 60 per second. So that's going to be needing 60 inputs from this. That's already one inserter. So then we're going to need more than that for sure to craft this, because it's 1-to-1. So each one of these can pull 60 items off of a belt. So let's go ahead and add a second one to start feeding this, even though this is only going to need 40 raw material or raw gears per second. That's going to be plenty for what we're going to need. So then just this one inserter is enough for that, and enough for covering both of these cases. Cool. So next, what I'm going to want is I'm going to want some way to insert into here the electronic circuit. So we have some room. We could side load it like this here, which would be kind of cool. So we could do this and then insert this here, and then I just need some way to bring this in. So let's say we do this here. And the reason that this is nice, because this allows me now to pull here, so it has a slight preference to pull on this side of the belt rather than on the inside, so just to kind of help with balancing this. So I'll go ahead and do that as a trick. Next thing is I'm going to need something that is going to input this here. So let's go ahead and do this. And I think we can get away with just the one. So that's perfectly fine. And then I'm going to try to use direct insertion as much as possible on this particular build. So we can put this electric furnace here and output it somewhere like that. Cool. So then this should have enough for us to insert everything in. So I'm going to go ahead and pull this as far out as possible, just to give us a little bit of help here. And just for this, I'm not going to need too much of this material, but I just want to kind of simulate it just so that we have it. So let's go ahead and add input. Perfect. And let's just bring this over here somewhere just so that we're showing that's working. Cool. Next, what I'm missing here, this is going to be enough to craft into here. You can pull this in. This is going to be iron plates. Okay, so iron plates are going to need to be here. So the iron plates themselves are also going to have to go into this, because this is still missing a source of that. So to make this flippable, I kind of am going to have probably 2 inputs on both sides here. So let's just simulate this here. And I'm going to say, let's just keep this simple and start with that. So as an input, I'm going to want here iron plates. And then that gets kicked off and is going. Perfect. So I'm going to definitely need beacons, because this is all way too slow. So I'm going to grab a beacon from up here, and let's go ahead and put this, I don't know, just somewhere. So let's just start shoving these in here. That's perfectly fine. Okay, so that's running, and I'm realizing I'm going to need an output. All right, there we go. And let's monitor this. So since this is going to then be coming in here, that's perfect. So we can fit a couple more beacons in. I would like to squeeze as many beacons in here as possible, because I could fit one here and here, but then this becomes an issue with this belt. So what I think we could do is we could just insert this here and then wrap this around so that it comes up and then over. That's perfect. There we go. There's also the slight bonus that inserters have in terms of swing time when they're pulling out of a turbo underground belt, but probably not enough for us to notice in this particular case. So, cool. So now this is very slow up here, so let's go ahead and add some beacons. And again, I'm just going to try to cram as many beacons as possible into here. So there we go. And this is making well over the 60 items per second that we need, and is backing up. Cool, great. So I'd like to also have as many furnaces around, or many beacons around this as possible. So what I'm thinking we're going to do is I'm going to bring these down and get that all nicely connected inside here. And then what I'm going to do just is I'm going to take this. And the nice part is, I think once we flip this around, yeah, that's great. So then we have room for beacons in here. Awesome. So I don't need this. I'll just model this after this here. So perfect. Now we have beacons all impacting this. This is way overkill in terms of speed. That means that it's just not running very often, which is already helpful. So even before adding inserters to kind of limit these little pulses that you're seeing, just making them run way faster than the downstream supplied item that is needed is already a big bonus. So perfect. Let's copy this and we will flip this around and I will add this as an input. So let's see if we can get away with 240 items per second coming in. So in theory, in order for this to be 240, really 60 items per second, because that's all we really need to supply, let's try to put a red belt in here. A red belt is going to carry 30 items per second, so stacked each half lane would be 15 times 4, so that's going to be a total of 60 items per second. So really, that is actually perfect for us. I'm just using green belts for everything, but red is going to be good enough to simulate that we're actually fully running here. So what's happening now, and we've got now both of these supplied down here. This seems all to be good. We can add some additional logic in here to just limit how often these are swinging, but we're oversupplying, everything's backing up, great. So this is perfect for producing the 60 items per second that we need. We can figure out where this is going to come later, that's fine. We can bring it maybe from down here or something, just something that fits in the widths. I guess we could just do that now, there's no real harm in that. We could bring this up one more, like this, and then maybe I could, let's see. Could I fit this somehow inside here? I can't quite fit. Yeah. I'm gonna go ahead and just say this is gonna be good enough. I will bring this in here like this, and then bring this around, and then just bring it to the other side. That is fine. We could even do probably this. Nah, this will be at least semi-symmetrical. Here we go. Now we don't need any more inputs, so we'll assume this comes from somewhere down here. That's fine. So the next thing then is we have now a module that's going to craft everything that we need. Let's figure out ratio-wise how much is actually going to go on this belt. We could do some math, or we could just easily just turn this off and just see does half a lane supply this, because that'd be really nice, because then I just need one 240 per second furnace stack. We're already seeing this is getting choked out. There's not enough supply down here to make the green circuits, and ultimately this is going to slow down to the point where we're not getting enough and we're getting a trickle. So this is a problem. So I know it's somewhere between 240 and 120 items per second, right? That's what we're going to be bringing in. But then I can probably calculate that a little bit easier. So we know that this by itself, right, 2 times this is the actual amount that we need. So that means that we're going to need 40 iron plates. We're also going to need to craft the gears, and since it's a 1-to-1 ratio with legendary productivity, that means that we need a total combined input of raw 80 items per second. So really though, realistically, they can come from both belts, so that's going to pull from here a total of half of that, so it's really just 40 total inputs that we're going to need. So that's 40 iron plates. Then this is going to need here, when it's crafting 60 items per second, that's going to be 60 iron plates, and I don't know, we'll put this here to be kind of close enough so we can look at it. Yeah, that's close enough. So this is going to be 60 items, so it's going to be 120 total iron plates. That's already half a belt over, more than half a belt. So that makes sense why this got started to slow down up here. So then we add the 120 items that we're going to need total, plus this, which we agreed upon was 40, so that's 160. And then all we got to figure out is the last one that's consuming this, which is here, and that is our electronic circuits. So ratio-wise, we know that that's going to be 250 here, so let's divide that by 2, so that's close enough. Really, let's just assume it's 45-ish. So 45, I don't know, like that's probably good enough. 40, something like that. I guess we could say it's a little bit closer to it. When the productivity modules get into play, it gets a little bit harder to figure out exactly how much you need. So just running some numbers here will help. 43, whatever. We'll call it 45. That's fine. So 45, 40, 85, and then we need 120 in here. So we're looking at a total of 205 materials that are going in this belt. All right, so for crafting the iron plates, I'm going to go through here and grab one of the lead follower designs that we created in a previous video. And what I'm going to do is I'm going to go ahead and just feed the inputs here for this. And let's go and feed that. So we know that we're going to need to be making 205 items per second. So by default right now, this is going to make 157. Each one of these makes 52 per second respectively. So we can get away with it, I think, if we just use 4 of these. So I'm going to slightly change this design around so that we can fit all of the furnaces in here so that we can craft the higher items. So the easiest option there is I'll just take this as the final output here module, and then I want it so that they're evenly applying to both sides. So these inserters will put them on the outside, and then we'll take this one and this will be on the inside. So this here, both of these are going to go in the inside belt. All right, that's perfect. So I'm going to copy this, bring this back in like this, and then I just need to connect the wires up again just to have the lead follower circuit conditions all active here. So that's pretty easy. Then after we've gotten this put in place, I think we can already go ahead and use this design. I don't think I have to modify it any more than this, but this will be enough to get us the throughput that we need. And then what I'm thinking is, instead of having them merge, I will just let them go ahead and just flow naturally. But one thing that I think is going to become a problem with this is that, and let's see, I need to connect the green wire across. So let's go ahead and grab a substation so that we have enough power. So here and here, and then we can figure out the power situation later for the other one. So just need to connect the green wires across. Great. So I know this is going to take more. I already know this, just over 120 items per second. So what I'm thinking I'm going to do is I'm going to remove this, and I'm just, for now, I'm going to assume that we have 240 items per second. It won't need this much, but I'm just going to go ahead and feed it. And then that will guarantee that we are supplying the amount that we need on the end for this particular side in this bank. So, okay, so that's going to be the module. So the next thing I'm going to do is the 2 different designs that we've come up with. So this head module we've already talked about, and then this design here. So I'm going to take this and I'm going to place this somewhere. So let's place this here and see how close I can get this. So, okay, so that actually could fit pretty nicely right there, but I need a little bit more space for these to come out. So let me see if I can redesign this slightly so that I can get this to feed in pretty nicely and make this kind of compact. So I'm going to not worry about this input here. And then I will delete this for a second, and let's see if I can get this to line up. So I'd like this in here like this. And then same thing over on this side respectively. I guess I could move these around because that actually lines up really nicely with these bottom pieces. And let's delete this for a second. And then I could come up and around and bring this over like this. So then that'll work. And then I could place this. I still would like this beacon affecting this if I can. So maybe this is just overkill. I'm trying to decide, or do we really even need it? This is making 100. No, this is way over the amount that it's going to need anyway. So this is fine. We'll just leave this as this design, and then I will copy and paste this over onto the other side. I mean, that extra beacon is not absolutely necessary because it's going to slow down anyway running. So that will work, and then I can just go ahead and delete this. And really at the end then what I could do is I could just have these in their original locations and move this over here. And then these will come in, let's say like this. And then we'll copy this on this side, and this would come over, up, and in. So that's perfect. So we'll press H, flip it, put it on the other side. There we go. Let's move this in a little bit. What this will look like now is we can place this already here. And then this will bring in the items that we need. So now we can monitor this and see if this is all backing up. I do need a place for this copper to come in. So let's see where I can get. Okay, so this is where this whole beacon placement here is becoming somewhat of a challenge for me to get copper. Can I get maybe sneak copper this way instead? I could do that. Okay. And then I guess I could come in and around like this. Bring this over and then replicate it on this side. So then we'd have this as the input. Okay, so that'll clean this up. I won't need this anymore. And then to make this semi-symmetrical, we could come up one and like this, and that'll fit. Perfect. So that means I can delete this one, and then this is going to come in here like this, and then just bring it down as far as possible. Same thing here. There. Let's bring it down. And then this, perfect. Can I reach all the way down? Nope. So we'll need one more. So then like this. Cool. So then this here, and we can just minimize the amount of inputs just to make this obvious. And then this is going to be needing to be, instead of iron ore, this is going to be copper ore. Great. And then let's just simulate that here. Shift right click, shift left click. That's why I'm always using these constant combinators to make this easier. And also then afterwards, when I delete these things from the blueprint book, then it's obvious also for people what needs to be inserted, or inputted. Cool, so that's all been put in here. So now we have this output. So let's go ahead and monitor just like we had before. And we'll run it just at higher speed. Press F5 so that I can have showing the gaps in the belts. It makes it easy to kind of visualize it. So there's no gaps, that means that we're constantly supplying, and that's enough for our actual design. Cool. So then next what I'm going to do is I will delete this, and we will grab this head module here. So let's copy this and place it on the top here. So I could actually just bring this whole thing down at this point. So let's delete this. And this is nice because we already in the very beginning designed it with this whole entire design in mind. So, or rather the same width. So this all fits nicely as a one modular design here. And then I can take this, flip it, put it in here. Okay. So now let's monitor this for a little bit and let's see how this thing performs after it actually kicks up and starts running. Cool. It looks like that's running. There's the tiny little gaps are being fed by this extra end cap. And all of them are constantly working down here, which we expect. So none of the pink lights are active. We can also press F5 and show the active time, but they all seem to be active and working constantly. Great. Okay, so space-wise, I could bring this down one more. It doesn't really matter, but I do need to figure out power here next. So right now, this section's all fed with power, and we already ran this. So I could fit this up here and get one more block, and then I just need to cover this little area here that still needs power. So I could put this here, could put this here. Let's do this. So this will be perfectly fine. So we'll place that in there. Okay, so now zoom out. Everything has got power. Great. And then I will add a couple more things. So just I want some RoboPort coverage so that when I'm building this out, it has the ability to, I'd like it so that it fits the whole design. If I have it somewhere around here, I'm never going to get the full thing, so that's okay. So what I'll do then is I'll just try to get it as close as possible to fitting the whole thing down here. We'll just place it somewhere, doesn't really matter where. Place on the other side. And then I need to extend the RoboPort coverage to hit everything up here. So let's just go as far as possible. As far as possible. Good. So that's got RoboPort coverage. That's does mean that unfortunately I'm not going to be able to tile it perfectly, but I can tile it now just based on the RoboPorts. And that's perfectly fine. That's good enough for this design. It means I need more beacons, but I don't think that's going to matter from a UPS perspective. So cool. So now we got our lead follower furnaces here. You can just check that they're not getting wake signals. I don't have any in here, so I'm going to go and add a couple of those. I'd like to clock the inserters by using them. I'm thinking there's some that are going to benefit more so than others. So these here I think would benefit the most from it, just because they all are turning on and off a lot more frequently, and the same thing for these, because they're just when you're seeing a lot more of these blips. I think there's diminishing return when you only have one inserter, so the ones that are pulsing a lot are going to be the more beneficial, so we can start with those. And then I'm just going to use threshold logic for this. That just makes it super simple. So in this case, read contents, and I'm going to do this for the rest of them, just for the sake of time. I'm just going to show like one case, and then I'm going to do the same thresholding for all the rest of them. And if you're interested in it, of course, the blueprint will be linked in the video description below. You can copy and look at all the different decisions that I made, but we'll talk through this first one and then just work through here to here, and then I'll do the other ones off camera. So this one, I know that this is constantly going up with the copper cable usage, so I just want this to only insert, let's say, when this is less than 16 here. Then go ahead and pull something out of it. So there it will kick off and we'll go and insert. And I'm still seeing this pulsing, so one thing I could do is I could grab a decider combinator. This may be better or worse for UPS, I'm not exactly sure, but just adding one extra signal may not be that great, but if I use it for both sides, that might help. And I could probably even have this one follow this swing. So what I'm going to say here instead is, okay, we have two inputs. I care about copper cables and I care about this. So whenever this is less than, let's say 32 to keep a buffer in there, and this copper circuit here is less than 128, that's divisible by 16, then I'm going to send an activation signal of a check mark. So I'll say this here. So then instead, I'm not going to hook this up, and I'm going to say here, I want you to be enabled now when the check is greater than 0, and I need to go back to the normal quality. And I'm going to hook this up actually to all 4 of these and have the same condition. So let's see if this works out. So now we're now just totally relying on this to come out of here. So let's watch this one. So this is going down here. Copper cables are coming down. And this should be evenly pulling everything. And I need to say here, oh, greater than 0. That's important. So let's set this, set this, set this, and set this. Perfect. So now they're all swinging at the same time, and let's see that these are still outputting. Seems like that's good. So these all swing, and then that's perfectly fine. It looks like all I would care about is that this never has a buffer that's lower. And that should be okay, because as long as this is overproducing, well, overproducing respective to this is making 701 per second, but we're never going to be consuming that. We're only consuming up to 270 and really half of that. So this is oversupplied, this is oversupplied, this is oversupplied. So what we can do then is I can say here, I only want this to swing, then in this case to feed these. This has a lot less of a buffer in the copper cables that is actually being inserted into it. So for this one, I'm just gonna probably just wire up this directly. And I will say here, I guess you kind of need both conditions to be true. And I don't know how useful this is, because this seems to be activating every single time this is needed. The buffer isn't high, so I'm going to leave this as being active. I don't think there's going to be a huge benefit from it. Reading from the belt here, that kind of matters. And it seems like the stack size is much higher for iron plates, so I will go ahead and say when this is less than 64, I'm going to go ahead and swing. That seems to work out, and there's not too many activation signals compared to the one on the right. So that's already kind of an improvement, so cool, we'll use that one. And then finally, in here, I will add some extra logic to this, but this seems to be running constantly whenever this is actually crafting, and there aren't too many wake-ups and slow and stops because this is constantly needing to be fed. So again, I don't think these are going to benefit. These aren't pulsating too much, so I don't know if those are going to benefit all that much. And I think this is good. So this is kind of limiting these that aren't pulsing. So good. So I think that's good enough. I'm going to call that good enough for this design. I'll test it out, I'll add some more circuits too, and I'll include that in the benchmark, and then we can make a decision from there. So for the benchmark, we're going to be trying a couple different designs. This is the one that we just designed in this video so far. Create a slightly different configuration. That is, I've changed some of the logic, still has the same base inserter clocking on the top copper line, but then I've added a couple extra swings just here to input and output materials into the actual electronic circuit production. And then additionally just a slight different configuration here. So aesthetically it's the same. The only difference is I've added one more furnace. I don't think this is necessary, as I think this design is completely fine on the left. This is just, I was curious if having extra back pressure is helpful at all. Otherwise, I've created this absolute monstrosity here, which is using cargo wagons, and the reason I'm doing this is because I was just for fun kind of messing around with the mechanic here, where you can actually fit underneath these. If you have two lined up next to each other, you can actually fit 4 total stack inserters underneath this, and this works because this, if you hover over just perfectly and you hold shift for a while, eventually, and this is hard to do, that's why I have a blueprint for it, you'll eventually be able to place it like that. So if you do this, then you can fit on both sides 4 that will all evenly place it in, and then if I grab that blueprint there again, now you can have 4 basically inserting in between each of these different ones, so you can get technically 480 items per second through these. So I've experimented with that just for direct insertion, and this is a purely direct insertion build, and then it winds up feeding the same furnace stack on the top. All of them have the same one. This just makes 480 items per second. And then I have one more over here that's more of a traditional output that is taking 480 items per second instead, but we get the benefit of only needing one of these assembly machines making 120, and the same just needing 2 furnace stacks on the bottom. So curious about testing both of these out, and the convenient thing about this is that it's just one input of copper instead of having, it makes it clearer that we need very, very minimal copper here. So with that, I'm going to set up some benchmark files, and then we're going to get into the actual tests, and we'll talk about the results after. Here we are in one of the benchmark setups. I wanted to point this one out because this is one big difference here. You're seeing this random case where it starts to dump things out on the other side. What's interesting about this setup here is that this will turn on and off, basically throttling this based on the output that's needed. And you can see down here that this is just consuming ever so slowly, and so this actually turns on exactly for the amount of time that is needed downstream, and it's actually just happens that whenever this next swing happens and it happens to take a little bit more out of this, that it's going to trigger this condition here where it's going to get slightly below the value, and then it'll occasionally dump some extra little bit that it needs down the line, and we'll keep pulling it. You could technically fit this by using lane balancers like I'm using here. This is just because I know the consumption downstream is slightly over 240, so what I've done is I've just, instead of making them merge like I normally do, I've just set them in here and then just lane balance them so that there's less spacing. I don't know if that's better or worse for UPS, but the point is, like, this makes it at least all the way downstream, this is always full constantly. And then only needing one setup instead of having to have an extra miner. So this is then running all the time, whereas this one is just only turning on and off just occasionally when these furnaces need a little bit more. So I've copied every single one of these designs multiple times, so the target rate of production here is nominally 1.8 million or so that it's producing, and then double that, so 3.6, 3.7, somewhere around there, and if we were producing common science. So this is all the way spread out here. So I'm going to go ahead and get out of the editor, and I'm going to increase the speed to 64 just so we're capping out. And then this is going to be one of the save files. I'm going to go now and recreate this for all the rest of them, and then I'm going to go and talk through the results. So for the benchmarks, I've included the original science design that I showed in the beginning of the video running in the Megabase. And then otherwise, I've included all the other ones that we've talked about so far, those other 4 candidates. I wound up deciding that I'm going to be using a different script for running these. There is on the Technical Factorio Discord, there's a person whose username is Tappy. He wound up creating a GitHub repo where he already created a wonderful PowerShell script. So I've used this now as my base because it's just objectively a better script than the hacked one that I created together or cobbled together for this. So I've just created a small wrapper around here so that I can just execute it and I don't have to repeat myself multiple times. So All this does is just takes an input parameter of the number of ticks I'm going to run this for, the number of runs, and then a file pattern. And the only thing that I've done is just point Factorio to look at the current folder so I can keep these runs consistent and I don't have to save these save files in Factorio, as I'd like to manage all the save files here in my GitHub repo. So I ran this script here just a second ago, and the nice thing about his script is that it prints out everything nicely so I can see it as it's running. So kudos to him, go check him out. Otherwise, so what does that mean? Let's jump directly into the results. So let's go ahead and open this and go through it. So I listed the test scenario, which we covered already, and they're all targeting the same amount of logistic science produced per minute in each map. So what I've done here is the results are as follows, looks like. So we've got the Q2 green science wins. The 480 version was at 388 UPS. Running this, the cargo one is just slightly worse in terms of overall performance, capping out at 383. I'm very tempted to still use it because it's just for the memes, but maybe I'll use a mix of these two. But ultimately, this is going to be the blueprint that I'm going to be releasing. And if you want any of the other ones, you can go to my GitHub repo and copy any of these maps and get the blueprints from there. I'm only going to release an actual blueprint version of the best design that I've come up with. The 240 was worse overall, and it kind of makes sense just having a couple extra buildings, and so having extra assembly machines crafting the subcomponents, that makes sense that those are a little bit worse. Having that extra furnace did not help. So again, that's just showing the less buildings you have in general, the better. So, and then all of these are a huge improvement over, like I've already said, the pretty bad Q2 design that I had. So in terms of percent differences, since the UPS numbers don't mean very much, I've removed the worst performer, which was my original design, and that's always what I'm going to be doing, is just comparing it to what I had made in the past and seeing if it's better. So we're seeing an overall percent difference of 31.68%. That's not the percent improvement, but that's basically the percent difference in terms of the values. So this is 31.6% different. So that means that overall it has that much higher UPS. So the 31% difference is a pretty big difference. So we're going to be using that then for the actual base. And again, all these are included, and a blueprint will be linked down below for the best design. So we're back at the mega base now. We've implemented it here. So I made a couple different design choice differences. I wound up changing it so there's only one inserter clock controlling all of these here, and then one controlling all of these. There was some unevenness that I was getting when it was trying to output all the time, but we still just have one acting as the lead for when these should be swinging. So and that's mainly because these are running all the time, so this is what I kind of had said a little bit early in the videos, that I assumed that this wasn't going to help all that much for the setup, and that's kind of true. So when you're running basically at the max speed of the inserter, just relying on wakeless is fine, and to not introduce instability. I've made one change. I wound up using the new clocked version up here on the mining output coming from the ore that is being mined, at least the iron output ores here, and that's working pretty good. That's been actually starting and stopping, and you can see that actually completely stopping when it needs to, so that's already a nice improvement as well. And otherwise, the main reason that we did red science last week and that I did green science this week is I'm ultimately wanting to get to the point where I have automated and finished both green and red, and then ultimately get to blue and then to purple, because those are the ones that are running for every single science and for all the researches in the end game. So if I make the improvements for these first, we'll probably see the most gain across the board for all sciences. So I'm going to run kind of in terms of the schedule. And also just real quick, we were back at 4.4 million after draining all the science and putting it all back. So what is next? I'm planning on continuing on and doing the other 4 base sciences here on Novice, and once I'm done with that, we're going to run a benchmark of the full base, running just straight mining productivity. So stick around, subscribe, follow for more if you're interested in seeing that content. And I'll be doing that in a few weeks. Otherwise, if you made it this far in the video, thank you so much for watching and appreciate your attention span. My name is abucnasty, and I'll see you in the next video.